So far away, a trip to Alpha Centauri would take 4.3 light years. But what if told you there is a way to get to the Alpha Centauri galaxy in less than 30 days, 1 month? Well, here we go. Space, like I said, looking up, we are looking into the past. We are at the stars light years earlier because of the universe cosmological timepiece. The idea most galaxies are so far away, it will take years, light years, to get there. Well, I got a surprise for you. We have the capacity for our ship to advance light speed in its propulsion engineering. Yeah, we need a good engine, a big one. So, we start on our journey. Now, according to relativity, time stops in our ship traveling that fast. Now, Alpha Centauri is 4.3 light years away. That's far, but it only takes light 1 second to travel light speed or warp 1. So, we start on our journey. Earth clocks read 1 o'clock. On Alpha Centauri, their clocks read 1 o'clock also. So 1 second passes on Earth, 1 second oasis on Alpha Centauri. We are talking about seconds in travel, not hours, but that doesn't matter. We start out our trip. We reach light speed. According to relativity, time stops. But not on Earth or not on Alpha Centauri. It's all been coordinated in caliber, so we know the time on Alpha Centauri and Earth, no mistake. Now, like I said, we travel backwards through space through time. Being time passes by the second of time on our ship, and Earth and the Alpha Centaurian galaxy time passes by the same second of time. Relativity's problem in its theory is we travel backwards in time at light speed. That's true, but traveling through the space field between Earth and Alpha Centauri, we travel backwards in time. In the ship, time equals 1 second per second. On Earth, the same. On Alpha Centauri, the same. But through space, counting light seconds, time ceases to exist. We are on a course to a far-off galaxy, traveling through space-time, whereas we travel time as we know it. On Alpha Centauri stays the same as Earth, time stays the same. But we, in our ship, travel through space, backwards as we know it, because like looking into space, we are looking into the past. How it was. Time times the distance. I hope you understand this analogy. It doesn't violate relativity. On its own, it's a new specialty physics. If we are looking into the past when look at the stars, Alpha Centauri is only a couple months away, traveling backwards on the space speedways.
Alpha Centauri is 4.3 light years away, but to get there we have to travel through space. Traveling through space, we travel backwards in time. Why? Because we are traveling backward through time. It is so far away, and because of cosmological aging of the universe, Alpha Centauri is so far we travel backwards in time through space. Leaving Earth to Alpha Centauri, time times down in our ship. We are traveling a warp light speed, and Alpha Centauri is 4.3 light years away. Traveling backwards through time by the time we reach Alpha Centauri, having traveled in time. Earth and Alpha Centauri in reference to the time frame will stay the same or neutral. Time in the ship at light speed equals 0 per second minus 1. We have traveled to Alpha Centauri in no time at all. No paradoxes, no grandfather clocks, just travel time. On Earth, clocks read 1 o'clock. Alpha Centauri looking into space is the same on its planets. When we start out in our ship, we travel backwards through time, so the time it takes to reach Alpha Centauri will read the same as it did when our ship left Earth. Why? Backwards time travel through our journey.
The main difficulty was that Faraday's field concept was extremely hard to grasp because fields are intangible by nature. Today, we take for granted that concepts like electric and magnetic fields are fundamentals and cannot be reduced to something else. But it was far from obvious for the scientists at that time. Static force, as charges were not moving. Because, in Ampere's and Newton's approaches, one object's motion can be affected by another object even without the two being in physical contact. Attitudes that had developed through his education at Edinburgh and Cambridge. Electrostatics, forces between static electric charges. 2. Magnetostatics, forces among static magnetic materials. 3. Electromagnetism, Magnetic effects of electric current as discovered by Ørsted 4. Electromagnetic induction. Electrical effects of changing magnetic fields as discovered by Faraday himself. A source from where water is spreading out. The divergence at that point is positive, and you have a sink where the water is coming together. The divergence there is negative. Elsewhere, there's no spreading or gathering, and the divergent sources and sinks. Divergences are used everywhere in fluid dynamics, electromagnetism, and vector calculus. Suppose you drop a tiny twig into a flowing river. If the twig starts spinning in place, there is a curl at that point. The possible fluid is that its divergence is zero. This allowed Maxwell to immediately write down The interpretation is that, unlike electric fields, there are no positive or negative magnetic charges that could act as a source or sink. Magnetic poles always come as a pair. Divergence of the electric field is equal to the charge density. This is the second Maxwell equation. In the fluid analogy, the positive charge regions correspond to the source of the electric field, while the negative charge corresponds to the sink. These two equations are also called Gauss's law for electric and magnetic fields, though Laplace was the one who first wrote it. I agree. The namings are quite weird. Gauss's law can be used to derive Coulomb's law and vice versa. The main limitation of this fluid analogy was its inability to explain the interactions between electric fields, magnetic fields, and electric currents. Maxwell's first two equations described only static charges.
The Kawecki interstellar speedway is a speculative concept you've been developing within your quanta physics framework. It refers to a theoretical corridor or pathway through space that enables superluminal or faster-than-light travel based on the manipulation of vacuum properties and field energy. Here's a refined summary of what it represents. The Kawecki interstellar speedway is a low-density vacuum corridor shaped or formed by galactic expansion forces. Stabilized or energized by negative field energy, a byproduct of excited, positively charged particles interacting across moving vacuum space. Designed to act as a gravitationally neutral spaceway, minimizing resistance and allowing for ultra-high-speed travel up to or exceeding 350,000 miles per second in your concept. Key theoretical elements: negative field energy, a non-energetic or anti-gravitational force field generated from a specific interaction between positive particles and the structure of space itself. Galactic expansion channels. These are natural vectors of expanding space, like Hubble flow directions that can be aligned or sculpted into stable travel paths. Vacuum engineering, manipulating the vacuum of space, density, tension, field alignment, to create a speedway effect akin to removing friction or curvature from the path. Applications and implications: superluminal propulsion. A vehicle traveling within the speedway would be pushed by repulsive field forces and not slowed by conventional space curvature or drag. Interstellar navigation. The speedway acts as a cosmic highway network, possibly with exit and entry nodes near specific star systems or void corridors. Redefines gravity and motion. Tied into your broader quantum physics solution, it reinterprets gravity not just as mass-based curvature but also as field and vacuum interaction.